Hi everyone, welcome to Go Classes. In this lecture, we will see binary decomposition. So, what is a decomposition? You already know. If you have a relation R in which we have some attributes. So, for example, let's assume this is a relation schema R and let's assume these are the attributes. Then decomposition means we decompose this relation into sub-relations, into two or more sub-relations. So, for example, what I can do, I can divide this relation into three sub-relations. Okay, we can say that these two attributes A comma B, these are present in R1. These two are attributes B comma C, these are present in R2, and these attributes a comma c comma d, so these are present in R3. Now this is called a decomposition, so I can say that this is a decomposition of table R. So this is called decomposition of relation R. So this is the point, that we have a relation R in which we have some attributes. So this is our relation schema and we do the decomposition. So what we do, we divide this relation into two or more sub relations. So these are the sub relations that we have. So this relation we are dividing into three sub relations. Okay, and you can notice that these two attributes a comma b, these are present in R1, b comma c are present in R2, a c d, these are present in R3. So this is called decomposition of relation R. I can say that this is decomposition of relation R, a comma b, b comma c, a c d. Okay, so you can notice this and this both are same. So this is the decomposition of this relation R. Now in this decomposition we have three sub relations. Okay, so that is the reason this is called ternary decomposition. I can say that this decomposition is basically because we have three sub relations, so I can say that this is ternary decomposition, because number of sub relations is what? Number of sub relations is 3. So because we have three sub relations, so that is the reason this is called ternary sub relation, ternary decomposition. Okay, and you can notice there is a, what is the property of decomposition? In the decomposition always attributes must be preserved. So if we do the, you can notice in any decomposition, whatever decomposition you take, then if you do the R1 union R2 union R3 means, if you take the union of all the attributes, these are the attributes in R1, these are the attributes in R2, and these are the attributes in R3. If you take union of all these attributes, then you will get the attributes of R, then you will get all the attributes of R. This is called attribute preservation property, and this attribute preservation is a mandatory condition for any decomposition. I can say that in the definition of decomposition we have this attribute preservation. So remember this attribute preservation, this is a part of definition of a decomposition. So this attribute preservation property, this is a part of, I can say this is a part of decomposition definition. So we don't have to write it again and again, because in any decomposition, in any value decomposition, attribute preservation will always happen. So okay, you will never lose any attribute. Okay, so if you take the union of all the if you take the union of attributes in all the sub relations, then you will get all the attributes of this relation R. Okay, so I can say this attribute preservation property, okay, this attribute preservation property, this is a part of decomposition definition. Okay, so basically any decomposition you take, if you have a relation R which you are dividing into R1 R2 and so on Rk, if you say that this is a decomposition, if you say that this is a decomposition, then what will happen? If this is a decomposition, it means that all the attributes must be preserved. So if you take the union of attributes of all these sub relations, then you will get all the attributes of relation R. So R1, okay, attributes of R1 union attributes of R2 union and so on Rk. If you take the union of all the attributes of all the sub relations, then you will get all the attributes of R. This is called attribute preservation property. Okay, so attributes must always be preserved. This is called attributes preservation. Okay, so attribute preservation is a part of decomposition definition. Remember, we don't have to write it again and again. This will always happen in any decomposition. Okay, now you can notice that in this lecture we will talk about binary decomposition. So what is the binary decomposition? So binary decomposition means when you are dividing a relation into two sub-relations. So binary decomposition means you are dividing a relation R into two sub-relations R1 and R2, of course, such that all the attributes are preserved. So if you take the union of the attributes of R1 and union of attributes of R2. So if you take the union of attributes of R1 comma R2, then you will get the attributes of R. So this is the part of, this is mandatory in any decomposition. So I can say this means this is a valid decomposition. So it implies that this is a valid decomposition. Okay, so this is the decomposition you can notice, and this type of decomposition is called binary decomposition because we are dividing the relation into two sub relations. So that is the reason this is called binary decomposition. Okay, now whenever you have binary decomposition or any decomposition, what we want it to be lossless. So any decomposition, you can notice the decomposition can be of two types. Any decomposition can be either it can be lossless or it can be lossy. Okay, so here we can say lossless means basically we are getting the exactly, okay, when you join the sub relations, then we get the, when we join the sub relations, then we should get our original relation. So basically these sub relations, when you join them, when you join the sub relations, all the sub relations, then okay, when you join them, all the sub relations, when you join them, then you should get your relation, your original relation you should get. Okay, and lossy relation means what it means, that you get some spurious tuples. Okay, so when you join the relations R1 R2 and so on, when you join all the sub relations, okay, then what you get some spurious tuples. So basically you get in this lossy decomposition, in this decomposition we get spurious tuples, we get extra, or I can say spurious, or I can say wrong tuples, spurious, or I can say okay, wrong tuples. Okay, so I can say we get spurious means extra tuples we get, and these tuples are not part of original relation. So you can notice these are called spurious tuples. So we get some spurious tuples in this situation. So any decomposition has two types, lossless comma lossy. Okay, lossless decomposition means that from this, from these sub relations, when you combine these sub relations, you will get your original relation. Okay, when you combine these sub relations, then you will get your original relation. So you can notice this is called lossless. So we are not losing any information, and in this lossy we are losing information. Actually we are getting extra tuples, it means we are losing information. So here what we are doing, we are losing information. Here we are losing information. Remember, we are not losing any tuples, we are not losing any tuples, we are not losing any tuples. Okay, we are getting some extra tuples. Actually we are getting some spurious tuples, means I can say we are getting some extra tuples. So we are not losing any tuples, but because we are getting some extra tuples, we are getting some wrong information. So that is the reason we are losing the information, because we are getting wrong information. Okay, when we combine these sub relations, when we combine them, then we get some extra spurious tuples. So that is called losing information. Okay, so remember, we are not losing any tuples, we are getting spurious tuples, we are getting extra tuples. All the tuples of R we are getting, all the tuples of the original relation we are getting, but we are also getting some extra tuples, some extra wrong tuples also we get. So that is the reason we say that we are losing information. Okay, so this is the, okay, you can notice. So any decomposition has two types, lossless decomposition or lossy decomposition. Now binary decomposition, if you do a binary decomposition, then how can you say, okay, a binary decomposition is lossless or lossy? How to check it? So binary decomposition, whether this binary decomposition is lossless or lossy, this is lossless or lossy, how to check it? So I can say this is your, I can say this is testing, this is testing lossless or lossy for binary decomposition, testing lossless or lossy, testing lossless or lossy for binary decomposition. So if you have binary decomposition, then how can you check whether your decomposition is lossless or lossy? Okay, so in this, whenever you do any binary decomposition, means you are, okay, you are dividing a relation R into two sub relations R1 R2, such that attributes are preserved, because attributes must be preserved, attributes must always be preserved. Now when you do this binary decomposition, then this binary decomposition will be lossy. I can say this binary decomposition this binary decomposition will be, when we can say that this is lossless, this binary decomposition will be lossless if the common attribute is a key. So basically, in these sub relations R1 R2, in this decomposition, the common set of attributes, I can say R1 intersection R2 means the common part, this common part must be super key in either R1 or in R2. So this must be super key, this must be super key in either R1 or this must be super key in R2. Okay, so basically lossless, I can say this binary decomposition is lossless if the common part R1 intersection R2 that is super key in either R1 or in R2. In this situation, we will say that this decomposition, this binary decomposition is lossless. Okay, and you can notice the similar condition. And when can we say that this decomposition is lossy? When can we say that this decomposition is lossy? When the common attribute, I can say, okay, the common part R1 intersection R2, this is not a super key in R1, this is not a super key in R2. Okay, in this situation, this is not a super key in R1 and this is not a super key in R2. In this situation, we will say that your decomposition is lossy. Okay, so this is a very simple condition. This is a very simple condition for testing whether a binary decomposition is lossless or lossy. All you have to check is just find the common attributes, just find the common parts, common set of attributes you find, and you check whether that is super key in either R1 or R2. If it is super key in R1 or it is super key in R2, then we will say that decomposition is lossless. If it is neither super key in R1 nor super key in R2, then we will say that it is lossy. Okay, so this is the complete analysis, this is the complete, I can say, definition of binary decomposition. So you can notice if a binary decomposition is lossless or not, how to check it. This is what we have seen. So any decomposition if you have, then that any binary decomposition is lossless if either this happens or this happens. Mean the common set of attributes in R1 R2 that is super key in either R1 or in R2. In this situation, we will say that this binary decomposition is lossless. Otherwise, we will say that binary decomposition is lossy. Let us take one example. Consider this relation. So this is the original relation, you can notice. So here we can say this is your original relation R. So this is the original data that we have. So I can say this is the original relation R. Okay, and we are decomposing this relation into AC comma BC. So this relation we are decomposing into AC comma BC. So when we decompose this relation into AC comma BC, AC means basically we are getting A1 C1 A1 C2. So this is what we are getting here. And when we decompose BC means B1 C1 B2 C2. Okay, now you can notice when we join these two, so this is a sub relation, this is a sub relation. I can say that this is your relation, sub relation R2, this is your sub relation R1 R2, and this is R. Now you can notice when you join them, when you do the natural join, then what will happen? So the common attribute is C, and we can notice that because common attribute is C, so this tuple will join with this tuple and this tuple will join with this tuple because we are doing the natural join. So natural join means equality of the common attribute. So you can notice the common attribute is C. So we will check the equality of common attribute. You can notice here this attribute C has value C1. In this tuple also this attribute C has value C1. So that is the reason this tuple we will join with this tuple. Okay, similarly you can notice that this tuple we will join with this tuple. So finally what we will get? We will get our original data. So you can notice we got our original data again. So when we join the sub relations, we got our original data again. This is what we say. So this is, we say that lossless. We did not lose any information. Okay, remember we got the exactly same relations. The original relation we got as it is. So that this means that we are not losing any information. So that is the reason this is called lossless join. Okay, and this is what we have seen here. Lossless join means you are getting your same data you are getting. So you can notice in the lossless join, basically when you join the sub relations, all the sub relations when you join them, okay, all the sub relations when you join them, then you get your original data, you get your original relation. In lossy, what happens that when you join the sub relations, then you get spurious tuples, means extra tuples, means wrong tuples. Okay, so let's take another example of that. So for example, this relation R, you are decomposing into R1 comma R2. Now the decomposition is like this. We are decomposing as AB comma B, as AB comma AC. Okay, so here this is the original table, so I can say this is our original relation R. So this is the original relation, this is the original relation R, and we have decomposed this relation into two sub relations, R1 a comma b, R2 a comma c. Now these sub relations, when you join them, when you do the natural join, then what will happen? In the natural join you can notice the common attribute, the common attribute is actually a. So we can notice common attribute is a, so this tuple will join with this tuple, and similarly this tuple will also join with this tuple. We can also see this tuple will join with this tuple, and we can also see this tuple will join with this tuple. So finally we can see that we will get four tuples. You can notice in the original table, we already in the original table, in the original relation, we only have a1 b1 c1, a1 b2 c2. So basically this is our, I can say this is our original data. Okay, similarly a1 b2 c2, this is our original data. But you can notice this is wrong data we are getting. This is the spurious tuples. These are the spurious tuples we are getting. So two spurious tuples we are getting means we are getting wrong data. This is not the information that we have, because remember, you can notice in the original table we don't have this information. So I can say we are getting wrong data, we are getting wrong information. It means we are losing information. Okay, so finally I can say that because of these spurious tuples, we are losing information. We are not losing tuples, we are losing information. We are losing information, we are getting wrong information. Getting wrong information means we are losing information. Okay, so because we are getting extra data. So you can notice one thing here. Here actually the common attribute c, and the common attribute was c, and you can notice that c is a super key in this table. In this table, if you notice, in this relation c is actually the super key, because c1 c2, so this value of c is not repeating. So I can say in this relation R1, in this table R1, C is the super key. Similarly, in this table R2, C is also super key. So you can notice C is this common attribute C. This I can say that this R1 intersection R2 means this common attribute. This is a super key in R1. So that is the reason I can say that this decomposition is lossless, because this is the condition for lossless we have seen. Lossless means the common part, the R1 intersection R2 set of attributes which is common between R1 comma R2, that must be super key in either R1 or in R2. Okay, so this is the point here. So finally you can notice that here R1 intersection R2, this is a super key in R1. So that is the reason I can say this is enough to say that your decomposition is lossless. So our decomposition is lossless, and this is what we have seen from this example, that our decomposition is lossless. Similarly, here you can notice this in this table, the common attribute is A, and you can notice in this table, the common attribute A is not a super key, because you can notice this value is repeating. Here also this value is repeating. So finally, I can say that in this table, in both these tables, the common attribute A is not a super key. So I can say that R1 intersection R2, that does not determine R1. I can also say that R1 intersection R2, that is not a super key, in R2. So because the common part R1 intersection R2, the common part is not a super key in R1, also it is not a super key in R2. So that is the reason we are getting lossy decomposition. Okay, so let's take just one more example, we can take it. Okay, so this is the condition. So consider this example. In this example, you can notice the relation is RABCD. So this is the relation, and set of functional dependencies are given to you. So set of functional dependencies are A determines BC. Okay, so this is the set of functional dependencies. A is determining BC. And what we are doing, so in this relation schema, we have four attributes A, B, C, D. These are the functional dependencies. So you can notice A determines BC, and decomposition is R1 R2 A, B, C, A, D. So the decomposition is like this. Okay, A, B, C, C, D. So this is the decomposition R1 comma R2. So this is a binary decomposition. You can notice this is a binary decomposition A, B, C, A, D. Now, we can very easily see, first of all, this is a binary decomposition, because the original relation we are decomposing into two sub-relations. So this is a binary decomposition. You can also check that attributes are preserved, because all the attributes we have. So attributes are preserved, and this is a binary decomposition. Now let's check whether it is lossless or lossy. If you have a binary decomposition, Then how to check whether this binary decomposition is lossless or lossy? Very simple. Just find the common part, means R1 intersection R2. What is the set of attributes which is common? So here the set of common attributes is A. You can notice. So R1 ABC, R2 AD. So the set of common attributes is A. Now let's check what this A can determine. Okay, so in this set of functional dependency, let's check what A can determine. So find the transitive closure of A. The transitive closure of A will be ABC. So this is the transitive closure of A. You can very easily notice that A can determine ABC. So I can say that this can determine R1, means this A is the super key in relation R1, because you can notice in this relation R1 we have ABC three attributes, and you can notice A can determine ABC. So A can determine every attribute in this relation R1. So I can say that this A is a super key. This common the intersection R1 intersection R2, this is a super key in R1. So basically what I can say that R1 intersection R2, this is a super key in R1. So that is the reason we can say that this is a lossless decomposition. So the answer is this is a lossless decomposition. Let us take another example. You can check it out here. So this relation R is given to you. In this relation R, we have 5 attributes, and the set of functional dependencies is also given to you. So the set of functional dependencies, A determines BC, A determines BC, CD determines E, CD determines E, and also B determines D, and also we can notice E determines A. So this is the set of functional dependencies that is given to us. Okay, now what are the decomposition? So two decompositions are given to you. The decomposition D1 you have, so one sub relation has three attributes ABC. So these are the attributes in one sub relation, and in R2 we have these attributes A, D, E. So this is the decomposition. Now let us check this decomposition. First of all, this is a binary decomposition. You can very easily see this is a binary decomposition, because what we are doing, we are dividing the original relation R into two sub-relations. So we have two sub-relations ABC, ADE. Now let us check this binary decomposition. Is this lossless? So very simple, what you will do, you will find what is the common set of attributes. So R1 intersection R2 you will find. So the common set of attributes is only A. Now what you will check what this A can determine. So this A can determine A, B, C, B can determine D. So let's find the transitive closure of A. So the transitive closure of A will be A, B, C, D. CD can determine E. So CD can determine E. So we can notice A can determine everything. Actually, in this relation, A is one of the candidate keys. In this original relation, I can say A is candidate key. Now we can very easily see that this common set of attributes in R1 comma R2 means this R1 intersection R2 is A, and you can notice this A can determine R1, A can also determine R2. So this A can determine R1, of course A can also determine R2, but the point is very simple that this common part can determine either R1 or R2. So this common part means this A, this is a super key in R1, this is also a super key in R2, but one is enough. Okay, if it is a super key in R1, then that is enough to say that it is a lossless decomposition. So actually you can notice here that R1 intersection R2, this is a super key in relation R1. So that is the reason we can say that this decomposition is lossless. Okay, so this is the question. Now let us see another decomposition. For the same question, another decomposition is given A, B, C, C, D, E. So for this same question, another decomposition is given where this is A, B, C, and where another relation is C, D, E. So this is the decomposition given to you. Now again, this is a binary decomposition, and we know how to check whether a binary decomposition is lossless or lossy. Checking whether a binary decomposition is lossless or lossy, that is very simple. All you have to do is find the common set of attributes. So just find R1 intersection R2. Now this common set of attributes, so what is the common set of attributes here? That is C. Now what you do in this set of functional dependencies, you find out what C can determine. So find out the transitive closure of C. So if you find out transitive closure of C, you will find only C. C can only determine C. So you can notice C can only determine C. C cannot determine ABC. C cannot determine CDE. So I can say that this R1 intersection R2 means this C, this cannot determine ABC. So this cannot determine this relation R1, and this cannot determine this relation R2. So because this common attribute, this common set of attributes, so this R1 intersection R2 means this C, this is not a super key in R1, this is not a super key in R2. So that is the reason we can say that this is a lossy decomposition. So this decomposition is lossy. Okay. So this is all about the decomposition, the binary decomposition. So remember this condition, this will only apply when you have a binary decomposition. If you are dividing a relation into two sub-relations, so this relation R, if you are dividing into two sub-relations, then you can check for lossless. Okay, then you can check. Okay, now checking for lossless is very simple. So checking for lossless decomposition. This checking for lossless decomposition is very simple. All you have to do is find the common set of attributes, means find this R1 intersection R2 and check, is it a super key in R1 or R2? Is it a super key in R1 or R2? So all you have to do is just check this. If this is true, I can say, if this is true, then lossless, I can say. If this is true, then lossless, else it will be lossy. Okay, so this is the testing of lossless decomposition for binary decomposition. Remember, whenever you have binary decomposition, this is what you can do, this condition you can apply. Okay, this condition you can apply and you can check for lossless or lossy decomposition. Now what happens when you have, when you don't have a binary decomposition? So basically, how to check lossless decomposition in case of non-binary decomposition, this is a question. Okay, so you can notice, okay, how to check, this is a question you should think about. How to check, how to check lossless or lossy, how to check lossless or lossy decomposition in case of non-binary decomposition. So how to check whether your decomposition is lossless or lossy in case of, in case of non-binary decomposition, means if you divide your relation into three or more sub-relations, then how to check for lossless or lossy decomposition. Okay, so in case of non-binary decomposition, this is we will see in the next class, and this is very important because let me tell you, many students they have misconception in this topic. Okay, so we will see the algorithm, there is an algorithm. Okay, so in the next class we will see a algorithm, we will see a correct method, we will see this algorithm which is called chess algorithm. Okay, so this was given by this mathematician Chess. So this is called chess algorithm, and this algorithm we will study, and this algorithm will help us in finding out whether a decomposition, whether a non-binary decomposition. So if I give you a non-binary decomposition, means if I divide the relation into three or more set of sub relations, then how to check whether your decomposition is lossless or lossy. So that can be done using chess algorithm. Let me tell you here that many students they have doubt, they have misconception, they have wrong concepts, okay, about this scenario. When you do non-binary decomposition, then how to check whether you have lossless or lossy decomposition? So for that, the correct method is a chess algorithm. Okay, so this is what we will see in the next class. Okay, thank you everyone.